Okay, thanks. So what we look at today is dual decomposition. That's a way to solve a constraint optimization, a special class of constraint optimization problem where you can do some distributed processing. And I'll just go through the skeleton of dual decomposition. I will then show you application of where it's used, and you might find it interesting. Now, I'm skipping primal decomposition. Okay, so this is just an overview of how it works. Okay, so we have a problem of this form. It's a constraint optimization problem maximized with respect to this vector x, summation of f of k xk. Okay, so each xk is a scalar variable which is one element of this x, and this objective function is a summation of fk xk. Okay, and the constraint, I've simplified the constraint. There could be nonlinear constraints here, but the constraint is simple. Summation xk must be less than equal to c, some constant. Okay, now think of it this way. Suppose, like you guys are students and most of us are from Asia here, rice eaters. So I have a huge sack of rice, okay? And this C here is the capacity, the total rice that I have, okay? And each of you wants a certain quantity of rice based on something, okay? And you want to maximize this. Maybe if you have too much rice to carry, then you don't want that much. You need some specific amount of rice. So this, each of you is a K, and fk xk is what you want to maximize. Well, actually, I take it back. You'll see what you will be maximizing. Subject to, this is the total capacity. Okay, this is how much I have. This is a very simple example. I'll show you a practical problem with the energy grid. The good news is this sort of optimization problem can be decomposed using dual decomposition. Okay, so here's a main processor, and you have all these uppercase K subprocessors, and you notice the index K here. Okay, so each of these subprocessors only has knowledge of fk, its own function, f of k. Okay, and this we'll formulate as a constraint optimization problem. We'll find the Lagrangian, and as the name says, it's dual decomposition. So we'll find the dual of this optimization problem. Okay, and so the main processor, what it does is it takes care of the Lagrange multiplier. Okay, so this is how it will work. And let's go over the details. So subprocessor K handles fk xk. And the main processor handles constraint. This is the constraint. Okay, so the Lagrangian of this is given by this expression here, summation fk xk minus, since it's a maximization, so I put a minus here, minus lambda of this constraint, summation xk minus c. And this lambda must be greater than or equal to 0. Okay? So this is the Lagrangian. Now let's play around with these terms to see how we accomplish dual decomposition. So theta d is max with respect to x of this Lagrangian, right? We have to maximize with respect to x, then it's a function of lambda alone, which is equal to, now what I'm doing here is I'm separating out the terms which contain an x and those well, there's only one term here, the term that does not contain the x. So we have lambda c plus summation fk xk minus lambda of xk. Okay, so this is theta d, which you can see this is this expression here, max. We can, it's of this form, max with respect to f1 x1 minus lambda 1 x1 plus f2 x2 minus lambda x2 and so on, right? That's this, what the summation is, which is equal to, I can, as you can see here, this f1 x1 minus lambda x1 can be maximized separately with respect to x1. This f2 x2 minus lambda x2 can be maximized separately with respect to x2 and so on. Okay, so I bring the maximization inside. So we have theta d lambda equals lambda c plus summation of each of these maxima. Maximum of fk xk minus lambda xk. Now this is what the subprocessors will maximize, not fk xk, but this. Okay, maybe lambda is how much I will charge you for each pound of rice. Okay, so lambda will be the cost per pound of rice in that case, and you'll see that in the context of the energy grid. Okay, so which is also equal to, I'll use both forms of expression. Now suppose xk star is known. Okay, then this is what it boils down to, right? So we have two forms of expressions here. This will be maximized by the subprocessor, and the subprocessor will think that lambda is known. Okay, so they will only maximize this part. Each subprocessor will maximize one of these terms. And this will be used by the main processor. Okay, it will handle the lambda. And of course, the xk star is this. Okay, so we have these two expressions. I've here I've changed the arrangement of the terms a little bit, but so this is the set of the two terms containing lambda. Okay, and these terms, this is separate maximization containing xk, correct? And so this is the dual problem. And let me tell you, we've shown that in this case, the lambda star, theta d lambda star will be equal to theta p of x star. In other words, strong duality holds in this case. Okay, so min max will be the same as max min. If we swap max x and min lambda operations, then we'll get the same result. Anyway, so this is the dual problem. So what the main processor will do is, now here the main processor doesn't need this, correct? So it only handles these terms, and so the main processor will minimize this. Okay, now on the face of it, it looks like a trivial problem. It doesn't matter what the value of lambda is. Okay, as long as C equals summation k xk star. Okay, but what if C is not equal to summation xk star is one question. And the other question is, we need the value of lambda. Like I just gave you a simple example. Maybe it's how much I'll charge for each pound of rice. So everyone needs to know what lambda is. Okay, and each subprocessor, or each of you guys is a subprocessor, will try to maximize this. So the value of lambda actually needs to be known. Okay? So the main processor will be handling the lambda. And each subprocessor K will only handle an xk in this setup. So this is what each subprocessor will do. Xk star will be argmax with respect to xk of fk xk minus lambda xk. So each subprocessor will assume that lambda is known a priori. Okay, and here the main processor will receive the xk stars optimal, and then it'll adjust lambda again. Okay, it's an iterative process. You'll see that. Okay, so this is what this is equal to this, and this second term is equal to this, what the subprocessor and the main processors do. Okay, so this is what happens. This is the problem decomposition. This is the dual problem. Minimize with respect to lambda, maximize with respect to x of the Lagrangian. And so the main processor will try to minimize this with respect to lambda. Okay, and lambda in general will be a function of the xk stars. Okay, so it's not that simple a problem. And then the subprocessors k will, each of the subprocessor will try to maximize these. Any questions so far? Anyone? Okay, so this is the problem decomposition. This is what the main processor does, and this is what each subprocessor K does. Okay, now let's look at the outline of steps. Main processor receives xk star, and then it does minimization. And then it sends an updated lambda back to the subprocessors. This is the task of the main processor. Okay, there's one caveat in step 2. Each subprocessor receives updated lambda from the main processor. You see the direction of communication here, these channels. And then it performs some maximization with respect to xk. Each subprocessor K independently does it. And then each of them sends the xk star. Once the maximization is done, it relays the xk star back to the main processor. So the main processor, so this cycle starts all over again. This is what the main processor does. It receives all those xk stars and starts the process all over again, and then subprocessors. Okay, now here's what. The main processor will just do a single step of gradient descent. Okay, because this is an iterative process, right? The main processor does these 3 steps, and then the subprocessors implement these 3 steps, and then it goes back to the main processor and subprocessor, and so back and forth, back and forth, back and forth. Lambda should not change dramatically. Okay, because then it will throw the subprocessors. Each subprocessor will, in one iteration, each subprocessor had a xk star. Okay, if lambda jumps dramatically, then they'll have to start this maximization all over again from scratch. Okay, but if the change in lambda is small, then these processors will require maybe just 1 or 2 iterations. Okay, so that's why lambda should not change dramatically, which is why we just apply a single step of gradient descent here. So this is what happens. Okay, this is what the main processor does, and this is what the subprocessors do. Here, I've just replaced that minimization with respect to lambda with a single gradient increment on lambda. Okay, so this is theta d lambda, and this is, let's look at what this step 2 here will in fact do. Note that even in theta d lambda, we must take care of the fact that lambda is greater than or equal to 0. We all know why. It's an inequality, it's the dual corresponding to an inequality constraint. Okay, in the primal problem, to refresh your memories, you don't bother about whether x is feasible or not. But in the dual, only thing you need to take care of is that the lambdas are always greater than or equal to 0, not the mu's, the dual variables corresponding to equality constraints. But here we have a sole inequality constraint. Okay, so theta d, the derivative of theta d is, we have to perform some kind of a gradient descent on this. So ignore this because this is constant with respect to lambda. I've graded out. Is that visible here? Yeah, it is. So take the derivative with respect to lambda. So this is what we get. Partial theta d over partial lambda equals c minus summation of xk star. Okay, and now since lambda must be greater than or equal to 0, we have to apply projected gradient descent. And in this case, projected gradient descent is super simple. All we have to do is threshold it so that it's never negative. Okay, that's what this plus sign does. Takes the argument. If the argument is negative, then it returns a 0. Otherwise, it returns the argument itself. Okay, so this is how we will do the increment. So we take a step along the negative gradient. This is the gradient. So alpha is our gradient step size. And then we should get this using just gradient descent, right? Lambda equals lambda minus alpha times derivative of this. But we threshold it. Okay, it's a two-step process, but I just wrote it as one. Perform the gradient descent step and then project it back to the feasible region. This is projected gradient descent on the dual. Okay, so lambda, if it's negative, we make it 0. Otherwise, we don't do anything to this. So this is a single gradient descent step. Okay, and this is what, in fact, will happen in step 2 of the main processor. So here are these steps. Let's look at one cycle of this whole process. Each of the subprocessors, observe the direction of the arrows, each of these subprocessors sends an xk star to the main processor. Okay, so this is where the cycle begins. And then the main processor receives xk stars from all the subprocessors. Then it applies a single step of projected gradient descent on the dual with step size alpha. Okay, so the updated lambda is then sent back to the subprocessors. Observe the direction of these arrows have now changed. Okay, and then all the subprocessors receive the updated lambda in parallel, and then they independently do this maximization. And then this cycle starts all over again. They send the new xk stars back to the main processor. and the whole process starts all over again. Okay, any questions with this? It's a very simple idea, right? Okay, and note that in actual practice, it's not that simple. Each of these could be a vector, and you could have nonlinear constraints. So this could be, this could have more constraints. Okay, and it doesn't have to be a function of all the x's here. You can have multiple constraints, some constraint with respect to x1 and x3, and another constraint with respect to x2, x5, x6, and so on. You can have all sorts of constraints here. But the key is you have this, the objective function is decomposable into something like this in terms of the primal variables. Okay. So this is the trick in general. Okay, so now what I'll do is dual decomposition application to the energy grid. So this is what my group had been doing until 2020. Okay, and we applied this method to the energy grid. So some of you are in power systems, so you guys would appreciate this. So this is the energy grid of the future. Okay, we have power plant, the source of power, and then the substation. This will be the main processor. Okay, and then each of these is not really a house, but it's actually something called, so this is the main processor, these are the subprocessors. We will pretend that each is a house for simplicity. Okay. So, but in reality, this is called the DSO, or the substation is a DSO, distribution systems operator, and each of these is actually maybe a whole neighborhood containing a lot of houses. Okay. So this each of these subprocessors is called an aggregator, and it caters to a lot of households, and its optimization is done separately. Okay, it has some computing power with itself. Okay, so each subprocessor or aggregator is multiple houses, and that's why some optimization needs to be done separately. Okay, and now this is what happens. This is the main processor, the DSO, and all the aggregators are the subprocessors. So X is the amount of energy per unit hour or per 15 minutes or something. Okay, so it's the kilowatt hours required, total amount of energy. Okay, so now many of you guys know that one of my main research focuses on Multigen systems game theory. Okay, so this is based on game theory. So each of these aggregators does some kind of an auction algorithm, and then we've shown that it converges to some kind of a Nash equilibrium, which actually does the maximization of Fk minus lambda xk. Okay, so the main processor receives the bids. These are the bids. Bids would be, okay, we want to consume this much energy. My group of houses, each aggregator K will say, okay, we want this many kilowatt hours of energy. Okay, so each of them submits a bid. Okay, and then the DSO is the the main processor, right? So it performs a projected gradient step like this. Okay, now actually several iterations are necessary because there are a lot of hidden constraints here, nonlinear. They're very nonlinear constraints which I've excluded from this. Okay, then all the nonlinear, there's so many nonlinear constraints, transformer capacity, line capacity, because this is not so straightforward. This distribution system is maybe a whole city, so the transmission lines or distribution, and they have their own capacities. And there's something called budget balance, voltage drop. These are so many things that have to be taken care of. I'll tell you what budget balance is. Okay, and so it sends the unit cost of electricity to each aggregator. Lambda is, okay, how much I will charge per kilowatt hour. $0.10 per kilowatt hour or whatever. Okay, so that's lambda, the dual variable. And then other dual variables get added to lambda. These are like overheads due to all these constraints. So they will, the unit price of energy actually will have to address all these losses and voltage drops and blah, blah, blah. So lambda is not just a simple thing. And it's also, in general, different for each aggregator, because if an aggregator of a neighborhood is very far away from the substation, then the power loss will be, I square R loss will be higher, right? So each lambda is actually different in practice. Okay, and there are so many other active constraints. And so anyway, for example, aggregator responsible for voltage drop gets charged more. Anyway, so these are practical issues, but you understand what's going on basically, right? Think of this alone. Basically, these are just other add-ons, but you can still think about the original framework and ignore all these. So there's a scalar lambda that gets incremented using projected gradient descent, and then it sends the DSO sends it back to the aggregators. Okay, and then each aggregator has multiple consumers, their residential units, say homes, and homes in a neighborhood are served by one aggregator. I just told you, and each aggregator runs an auction algorithm. Okay, this is something beyond this course, but you know, every time you Google something, there's an online auction algorithm going on. It's called it's similar to something called a VCG auction. Victory got a Nobel for the auction. But this is slightly different. This is another auction. Now, a little bit about this. What happens is each aggregator or each subprocessor runs this, correct? Suppose each aggregator was just one house. Let's think of it this way. Okay, now Fk, Xk is some utility curve like this. Okay, on the x-axis we have amount of energy consumed, and on the y-axis you have f of x, which is how much utility you benefit. Okay, for instance, now, well, we don't have any of the lights turned on. Okay, it's all dark, except, but that's because I'm using the projector. But suppose it was pitch dark. Okay, just one lamp would make a huge difference, because then we can all see, right? So there will be huge benefit from 0 lamps to 1 lamp. Okay, the utility will go up quite a bit. But from the first lamp to the second lamp, if you turn on another lamp, okay, it gets brighter, but the utility, the gain is not that much, correct? So the gain will be less. And so you have this saturation. If there are 100 light bulbs, then the 101st hardly makes any difference at all. Okay, so it saturates. So it's actually a concave function like this. And what happens is they all try, each aggregate tries to maximize this. What is lambda xk? This is what they try to maximize, right? Now here, this is the total utility gained, what they want to maximize. And what is lambda is what? The unit cost of electricity, right? And so what is lambda times xk? The total amount one has to pay. Correct? So this is what they try to maximize. Xk is the energy consumed, and this Fk is the utility from the energy, and lambda is the unit cost of the energy. Okay, lambda Xk is how much total cost in dollars that this kth aggregator has to pay. Okay, and what the aggregator tried, why do they try to maximize this instead of just trying to maximize Fk of xk? Because that's the net payoff. This is how much they gain from consuming this much electricity, xk, and this is how much they pay for it, right? So this is, maybe this utility can be scaled in dollar terms. So it's utility in terms of dollars, and this is how much they lose financially, how much this is the gain, or perception-wise how much financially they gain, and this is how much they lose. Okay, and so this is the net gain. So that's why they try to maximize this. Okay, so this is, back to this. So the main processor receives bids from the aggregator, and it does this minimization and sees the total amount of energy available from the power plant. Okay, so this is what each aggregator does. It receives lambda from the DSO and maximizes its own payoff, which is utility minus price, and then sends updated demand xk star. Okay. Now, this was the main objective. Correct? Turning back to the optimization problem, this was the main objective. Summation k of fk xk. Now, what is, back to here, this is f of x is the total utility gained by a consumer. Okay. And so summation fkxk is the sum total of the utilities of everyone. That's called the social welfare. Okay, so what in fact is happening here is energy is getting distributed amongst all the processors, amongst subprocessors, or all the aggregators, such that the total benefit, it's called the social welfare, is maximized. And this is our constraint, the total resource allocated. That's C is the total resource available. It's a general framework, actually. This is the total resource available. Why is it cycling through all these? Okay. Oh, well, anyways, so this is all the list of publications, and well, actually, one paper got rejected because the reviewer was a moron. We used Pareto optimal. We tried to minimize two things. It's a vector function, two functions at a time, not just one function, two functions at a time. The second function being fairness. And what we did was developed a new multi-gradient descent approach. But a lot of these reviewers in power systems, they don't understand math. They're not good at math. And so this is not Pareto. Pareto, it's something that normal evolutionary algorithms do, but these guys didn't understand. We had the proof, mathematical proof that it's Pareto optimal. It went over their head. Anyway, so this is, and so there's actually another paper, and then we're trying to extend this research. But this is a gist of dual decomposition. Are there any questions? Do you understand what's happening here and why it's happening? From the example, you see what's the problem and why it's done this way. So we want to maximize the social welfare. Each of these is the utility gained by the kth, well, we'll just call it subprocessor. And this is the total resource available. Each xk is a resource consumed by subprocessor k. So what we are trying to maximize is the overall benefit. Summation of kxk, summation of all the utilities. Okay, and then, what's that? So back to here, forget all this.
What is the application of this decomposition? Like, if we do not decompose, still it will work, right?
Well, what happens is each subprocessor, this fk is not known. In our problem, fk is not available to the main processor. It's private information of each subprocessor. And in general, so actually look at one of the publications. We made a case out of that. Privacy, I think we added the term privacy preserving, with hidden user in double auction with hidden user information. Okay, any other questions? Generic questions not relevant to the theory.
Yeah, some question from the homework.
Oh, that's, sure. We'll address that later, but any questions pertaining to the slides? Okay, we'll end this lecture, and so